Hello, ladies and gentlemen. This is Unit 5 Notes Part 3 for our kinetics unit. This last set of notes is actually pretty short. There's only a few more things that I just have to go over with you. A couple of random things that we didn't really talk that much about throughout the unit that I would like to address here and now. The first is, what are the factors that can affect the rate constant K? So we already know, we're already familiar with rate constant K, and we know that it's part of a rate law expression. But basically, K is a constant value that basically addresses everything else about what can influence the rate of a reaction other than our actual reactant concentrations. Because when you mess with reaction concentrations, like these general reactants A and B, you're going to see that numerical value change in the rate law. But K represents everything else. So things like temperature can change the value of K. Things like lowering the activation energy, adding a catalyst. Things like improving reactant orientation. All of those factors that can change the rate of a reaction that again, do not actually change the concentration, are things that will change the value of K. So if you increase the temperature of a reaction, we know already that K is temperature dependent, so if we increase that temperature, K is going to increase, which will then increase the rate. If we add a catalyst, lowering our activation energy, that is also going to increase K, which again increases that rate. And then if we change our orientation of our reactants or give them better geometry somehow, that is also going to increase K, which increases our rate. And then again, doing the opposite of those things, so a decrease in temperature, raising the activation energy, or making our orientation of our reactants worse would do the exact opposite. So just be aware of those things, because quite often multiple choice questions are asked of you, which will be like, if we did this to the reaction, what effect does that have on K, and or what effect does that have on the rate of the overall reaction? So those are just things to be aware of. The next thing I want to discuss is the Maxwell Boltzmann distribution, which is another way that we can look at reactions and their energy. So overall, up until this point, we've been looking at potential energy diagrams, which you'll be familiar with because they look kind of like that, and we can track if those reactions are multi-step or single-step or endothermic or exothermic or what have you. But this particular distribution is a graph that we use to look at how much kinetic energy any particles of a sample have. And it's going to let us know if the majority of that sample is moving fast enough to overcome that reaction's activation energy or not. Okay? So if we look at this graph down here, we see that there are a few different lines. But let's explore what all the parts of this graph mean really quickly. The x-axis could be a couple of different things. Most often, you will probably see it as kinetic energy, just as it is listed down here. But sometimes you could also see it as velocity or speed. So I'm just going to write down kinetic energy, velocity, or speed. Those are the most common labels for that axis you could see. The y-axis over on this side here generally is just number of particles. All right? So those are the two axes you're dealing with on a graph like this. The three lines represented on this graph are not always present. It depends on how many temperatures or kinetic energies you're viewing your sample at. In this case, our red line here represents our lowest temperature particle distribution. So I'm just going to write that down, low temperature. That's our low temperature sample here. And at first glance, this graph can be a little bit confusing because the red one is our highest peak, and that usually doesn't correspond to low anything if it's your highest peak. But if you look at your axes, it kind of starts to make sense, because what this red line is telling you is that the highest distribution of particles here are moving very slowly, because we can see that that peak is right here, which is what, maybe 3 kilojoules per mole, and that is not a lot of kinetic energy. So what this red line is telling us is that most of the particles in that sample are moving very slowly. All right? Our green line that's dotted down here at the bottom is our high temperature sample. So we see a startling shift there. We see that the peak is not nearly as high, but we also see that this green line extends much farther into a higher zone of kinetic energy. So what's happening here is you increase the temperature of a sample. It's not that every single particle is moving the exact same amount faster. What you've done when you increase the temperature of a sample is you've increased the average particle speed. So we have more particles in this green line that are moving faster versus our red line that had most of them moving slower. And then our blue line, which is made up of those little dots, that's just kind of a medium temperature. Right? Our dotted line that's moving vertically in the middle here, that's actually labeled helpfully for you on this graph, is actually our activation energy. All right? So if we analyze this graph really quickly, we notice that with our red sample here, most of those molecules are not moving with enough kinetic energy to bypass this line. And we know that to react, our particles need to be hitting each other with enough energy to either meet or exceed our activation energy of that reaction. And like a good portion of the molecules in that sample are to the left of that line. So what that means is most of our particles will not react. There's only a small fraction of particles in that red sample that can actually react, and that's represented by this little shaded area under our curve, because the area under our curve represents our total number of molecules in that sample here. So again, only these molecules under the curve over here to the right of that dotted line actually have enough energy to hit each other and react with one another. We see in our medium temperature sample, in our blue line, that area under the curve is a little bit bigger. So as we increase the temperature, more of our molecular sample is moving fast enough to hit each other with enough force to actually react. And then with our high temperature sample over here, we notice that, hey, guess what? A much larger area of those total amount of molecules are moving with a significant amount of energy and have met or exceeded the collision energy required to actually react. So that is how you read a Maxwell Boltzmann distribution. We are looking for an area under the curve that is to the right of this cool little dotted line there. All right, so let's move on to the next section. What about catalysts and the Maxwell Boltzmann distribution? Because that does actually shift a little bit how you read the graph. So let's talk really briefly about catalysts and remind everyone what they are and what they do. A catalyst is something that is not actually used up in the overall reaction, is not technically part of it, but it is going to facilitate that reaction. And by and large, it is going to decrease the activation energy. That's the whole point of using a catalyst. We decrease the activation energy to make that reaction easier, right? And to increase our overall rate. Catalysts can be of a couple of subtypes, right? They could be homogeneous or homogeneous catalysts, which basically means that the catalyst that you're using is in the same phase as the reactants of the actual reaction. Or that catalyst could be heterogeneous or heterogeneous, meaning that the catalyst itself is in a different phase than the reactants that it is catalyzing. So to just get an idea of what I mean by that, recall the demo that I did with the decomposition of hydrogen peroxide, which is this equation right here. We saw that hydrogen peroxide was just sitting in that Erlenmeyer flask, not really doing much. And then I added that solid powder. That powder was manganese dioxide, and since it is a solid powder, it was in a different phase than the aqueous hydrogen peroxide that was decomposing, and so that would be a heterogeneous catalyst or a heterogeneous catalyst because it's in a different phase. That's literally all that those two terms mean, but it catalyzes it the exact same way. It facilitates that reaction to move forward by lowering the activation energy. All right. So let's take a quick look at the Maxwell Boltzmann distribution. So again, we have our three lines here. We have our red line that represents our low energy sample. We have our blue line that's our medium energy, and our green line that's our high energy or high temperature sample. So this time we have two dotted lines. We have our normal dotted line, which just represents the normal activation energy of that reaction. And we see that the area under the curve of our green line over here represents the amount of particles in that sample that are hitting each other with enough energy to react. But if we add a catalyst, what happens is that activation energy line shifts to a lower amount of kinetic energy. So we're seeing that over here. So suddenly in our green sample, because we've added a catalyst and we've reduced the amount of energy they need to hit each other with, we see that a much larger percentage of that sample is able to react, and that will speed up the reaction overall. All right. Over here, let's compare that really quickly with our potential energy graph that we've seen a bunch of times. We see that our black line here represents our uncatalyzed reaction with its much larger activation energy. And we see that this little blue line, multi-step one, represents our catalyzed reaction. But our activation energy of that catalyzed reaction is much lower, just like how we saw it lowered over in the Maxwell Boltzmann distribution. Okay, so that's pretty much all about Maxwell Boltzmann and how you read them and interpret them. Moving on to our multi-step reaction mechanisms again, I had said previously that we were going to look at what happens when you have to get rid of an intermediate that happens to be in our slow step. So let's just briefly remind ourselves, what do we know about reaction mechanisms so far? We know that our reaction mechanism is made up of elementary single-step reactions. We also know that the rate law of our overall multi-step reaction should reflect the rate law of the slow step of our mechanism. But we are also told that we can't have any intermediates in the rate law. And when there's an intermediate in the slow step, sometimes you have to do a little bit of substitution with the rest of your steps in the mechanism. Okay? So when our slow step of our reaction mechanism has an intermediate, we have to switch the mechanism up, switch some things around to substitute other chemicals out for that intermediate. And the only way we can do that is with a fast equilibrium step. Now, what is equilibrium? I've talked about it a couple of times, but just to give you a definition, an equilibrium reaction is a reversible reaction. And it's recognizable because you're going to see this little double-pronged arrow showing a forward and a reverse reaction. When a reaction or a reaction step is at equilibrium, the rate of the forward reaction is equivalent to the rate of the reverse reaction. That's why we see that double arrow there. And why that's important here is because you can do mathematical substitution to sub out other chemicals for the intermediate you're trying to get rid of. So let's pretend for a second down here that this is our fast equilibrium step. And this thing, CH3OH2, is the intermediate that we're seeing in our slow step that we have to get rid of. Now, obviously, the slow step is not shown here, right? This is literally just me showing you a fast equilibrium step that we are capable of doing substitution with. So assuming I have to get rid of this thing later, that means that I need to use this fast equilibrium step to solve for it, for lack of a better term. So we see two things here. We see a K1 and a K negative 1. K sub 1 represents the forward reaction, and K to the sub negative 1 represents the reverse reaction. So if I were to write a rate law for my forward reaction, that's again the one going to the right here, that would be what you're seeing in blue down here. I would see that the rate of that forward reaction is K1 times the concentration of this reactant times the concentration of that reactant, which is what we're seeing here. However, if I were to write a rate law for the reverse reaction going the other way, I would use that the rate of the reverse reaction is K sub negative 1 times the concentration of this, because that's the reactant for our reverse reaction, okay? Once I have that information, the fact that this is an equilibrium reaction means that I can set those two expressions equal to one another, and I can solve for the intermediate that I'm trying to get rid of somewhere else. So I'm just going to show you how that works real quick. We have our K1 on this side, and we're going to set that equal to our reverse reaction. All right, and all we're going to do is we're going to isolate the thing that we're trying to get rid of somewhere else. So I'm going to go ahead and divide both sides by K to the negative 1. And I get that my intermediate, CH3OH2 plus, is equal to this new expression over here. So I'm going to rewrite it. Now, once I have this, I can substitute this expression in for this intermediate somewhere else where I need to get rid of it. That's what this whole process is for. So let's do that. Let's look at an overall mechanism, and I'll walk you through this practice problem to see how that works. Our practice problem says, determine the rate law expression predicted from the following proposed mechanism. So we already know that usually when we write a rate law, we're going to be writing a rate law that matches the slow step of this reaction mechanism, right? Because we know our rate law of our overall reaction needs to reflect our slow step. So let's write that rate law really quick. Rate is equal to our concentration of this reactant of our slow step, O3, times our concentration of our second reactant, O. All right? But the problem is, if we look at our overall mechanism, O is an intermediate. So normally we would cross that out, and we cannot include it in the overall rate law because our previous set of notes told you not to. But that doesn't mean that that intermediate doesn't influence the rate. It means we can't include it since it's not a part of the overall reaction. Okay? So we are going to use this cool fast equilibrium step up here to sub out for this intermediate in our rate law. So over here, keeping in mind that I'm trying to sub out for this thing, we're going to set our forward and our reverse reactions equal to one another. If I were going to write a rate law for that forward reaction, I would say that the rate is equal to K sub 1 times our concentration of O3, right? And we're going to set that equal to the rate of the reverse reaction. And our rate of our reverse reaction would be K sub negative 1 times our concentration of O2 times our concentration of that intermediate. All right? Now, remember, we're trying to sub out for the intermediate, so we are going to solve for that thing. We're going to do that by dividing both sides of this expression by K negative 1 and O2. All right? Those are going to go away on our right side, and we are going to get that our concentration of O is equal to K1 over K negative 1, and then our concentration of O3 divided by O2. Now, again, now that I have this expression, I can literally plunk it in and replace it in my rate law so that I no longer have an intermediate in that rate law. Okay? So, I'm going to rewrite that over here. Our rate is equal to our existing part of the rate law, so that's O3. I'm going to put that in parentheses over here. And then I put in the rest of my expression. Oops, over here I forgot to include the first K. All right, so now we have an overall complex expression, so let's just talk about where those parts came from so nobody gets lost. This first part here, our rate equals K times O3. That came from our original slow step rate law. And then this second part over here came from that substitution that we did. So now all that's left is to simplify that really complicated looking expression so that we can write our final rate law. We can put all of our like terms together. So all these K's should really go together over here. And what we're going to do is we are going to rewrite K in a more simplistic manner, right? Because all of these K's are constant numbers and we also don't know what they are. So we always tend to put all those K's and lump them together. There's a couple of different ways you can lump them together. I personally prefer just saying K prime, and K prime is like an observed K. Because again, we don't know what that thing is. It's kind of like in calculus when you just say plus C at the end of an integration because there's some constant value that you do not know. And so we just lump all of our K's together into a K prime. Beyond that, we just need to simplify the rest of it. So I see that there's two O3s here that are being multiplied together. So we're going to call that concentration of O3 squared. And then we see that our O2 is still on the bottom, so we're going to write our concentration of O2. And this is my new overall rate law for this multi-step reaction mechanism, which I'm sure is a little bit confusing, but just bear with me. We're going to do another example so you can get more used to this. All right. So we have this next practice problem. It says a mechanism has been proposed for the following reaction. And we see that the reaction is chlorine gas plus CHCl3 yields hydrochloric acid and carbon tetrachloride. Okay, so that is our overall reaction, which we did not have to figure out. We were given that information. In the table below, we see that there is a multi-step reaction profile, or our multi-step mechanism, and we see that our slow step is right here in the middle, step 2. Question A says, does the overall balanced equation from the mechanism agree with the given stoichiometry? Justify your answer. Okay, so that sounds complicated, but really all that it's asking is, hey, does this 3-step mechanism match up with my overall reaction? So all we got to do is we have to cross out any catalysts and intermediates that we see and see if when summing those steps together, we get the same thing as the problem gave us. So I see that chlorine is appearing on the right, and it's also appearing a couple of times later on the left. So that would be an intermediate that gets crossed out. I see that CCl3 is doing the exact same thing. So those are, again, intermediates that get crossed out. So if we sum that overall reaction together, we would get Cl2 plus CHCl3. That's these guys on the left, and then we would get HCl plus CCl4 on the right, and that's those two guys that were left over. Since this summed reaction matches with what we were given at the top, we can say for letter A overall, yes, absolutely this thing matches with the given stoichiometry, because when those 3 mechanism steps are summed together, you get the overall reaction that the problem gave. So, yes. And then my reasoning would be something that you could write down for that. All right. I'm going to go ahead and erase all of this fun stuff so that we can see everything when we do the rest of it. All right. Part B says to identify any intermediates and catalysts. Well, when I went through to sum everything up together, the only thing that I found was intermediates, not catalysts, and that was, as a reminder, the chlorine and the carbon trichloride. So our intermediates are these two. It does not ask you to justify anything, so you can literally just list them. All right. Our next part says determine the rate law. So here's where it starts to get a little bit more complicated. Once again, we know already that our rate law for the overall reaction should match my slow step. So what I'm going to do up in this corner is I'm just going to really quickly write a rate law for that reaction. So our rate is going to be equal to K, and I'm going to call that K2 specifically because this is step 2 and it'll help me differentiate my Ks later. And so our rate is equal to K2 times our concentration of both reactants in that step. So we have chlorine and we have CHCl3. All right, and I'm going to put a little star above chlorine because chlorine is the intermediate that we cannot have in that rate law. So that is the thing that we are going to use our fast equilibrium step, recognized by that double-pronged arrow, to get rid of. Okay, so next part, we have to write our 2 rate law expressions for the forward and reverse reaction of step 1. So our forward reaction would be K1 times our concentration of Cl2, and we're going to set that equal to our reverse reaction, which would be, K sub -1 times our chlorine. Now, because there is a 2 here, that means that the reverse reaction is actually bimolecular. And when that happens, you actually move the coefficient up to become that exponent, expressing that the reactant order for the reverse reaction is second. That becomes important later. Okay. Once again, we are trying to solve for the intermediate, which is chlorine. So we are going to try to isolate chlorine on that right-hand side. And we're going to do that by dividing both sides by K sub -1. And we get that K1 over K -1 times the concentration of Cl2 is equal to our concentration of chlorine squared. Now, we are going to square root both sides of both of those things. I'm going to express it as raising it to the power of 1/2, which means the exact same thing. So I'm just going to go ahead and raise both sides to the 1/2 power. And as we know, doing that gets rid of it on this side, and we get that our concentration of chlorine is equal to K1 over K -1, and I'm going to raise that to the 1/2. And then our concentration of Cl2 also raised to the 1/2. And again, I separated those specifically because we have to sub some stuff out and rearrange our terms, so it's just easier that way. Now, this expression that I just isolated here is going to get plugged in for our intermediate, but everything else needs to stay. So I get that my rate is equal to K2, and then I'm going to put the rest of my K values in there. And then I have the rest of this substituted in expression. I have my concentration of Cl2 raised to the 1/2, and then my concentration of CHCl3. All right, and again, that looks like a very, very complex rate law expression. So remember that we can always rewrite that, and we can combine our cool K values. And we're going to say that our rate is equal to K prime. And we are going to put in our concentration of Cl2 to the 1/2 times our concentration of CHCl3 as my simplified rate law. And that would be my answer. Now, question D asks us to write an expression for the observed rate constant in terms of rate constants from the proposed mechanism. Again, sounds complicated. It's not. You literally already did it. So all we have to do now is bring this complicated looking K expression down, and we say that our K observed, which as a reminder is another way to write K prime, which is my favorite way to write it. So K prime would be equal to that complicated looking expression. You would use K2 times K1 over K to the -1, all raised to the 1/2 power. And this is your expression for the observed rate constant. Okay? If you have any questions, please let me know. I'm happy to answer them for you in class.